Okay, now we're going to list a few more special properties for these definite integrals. And we're not going to go through proofs of any of these, but since we can interpret these as Riemann sums, then we might be able to at least intuitively see why the answers are what they are. From A to A, essentially the delta x is a 0. So we have nothing. We have no integration happening at all. Whether it be area as your interpretation or just a Riemann sum, our delta x is a 0. Okay, if f is integrable on AB, okay, in other words, we can find that the limit of that Riemann sum, okay, then if we switch the limits of integration, B to A, it becomes the opposite of A to B. So if you think about that, it has a lot to do with how the delta x is formed. If we interpret this as a Riemann sum, because delta x is the upper limit minus the lower limit. So if you switch that, then you're going to have the opposite, and you will have your delta x will be opposite, which will introduce a negative sign into the computation. All right, so another one, here it is. We can break an integral up into as many pieces as we want in here. In other words, I can break this into 2 pieces in this case, whereas as long as c is the upper limit of the first integral and c is the lower limit of the second integral, and of course a begins at a and finishes at b. Now normally starts at a, ends at b. Normally you would do this if you wanted to break a function into 2 pieces. Possibly 1 piece is easier to integrate than 2 together. But it turns out that c, it can be any number. So it doesn't have to be between a and b, although that's probably one of the more useful interpretations here. Next one. If you have a constant stuck in there times a function, all it does is multiply times that definite integral k. If you have the sum of 2 functions, you can break them into the sum of 2 definite integrals. If you know that your integral is greater than or equal to 0, well, sorry, your integral will be greater than or equal to 0 as long as f of x is greater than or equal to 0. That will always be true. Your definite integral of f will be less than or equal to the definite integral of g on the same interval, as long as f is less than or equal to g. Okay. What else do we have here? We'll have an exercise with some of these in a minute. Okay. All right, here's a little example where we can use a bit of this, of these properties. Okay, let's see. We want to integrate, find this definite integral in here. And we're given these other pieces up here. Here's one that I can use. And I can use this one. Okay, now this integral from -1 to 1 f dx can be -1 to 0 f dx plus 0 to 1 f dx. We can break it that way. And the reason I chose that is because of this right here. I see I'm trying to calculate that. So here's that integral right here. And I know this number here is a 10, and I know this number is a 5. So this is my unknown in here. I'll just call this I, the integral. So that integral must be a 5. You can see that. In other words, I must be a 5. So that's it. It's just a little bit of algebra using geometry of the definite integrals and that property. Okay, this one here, I know this part is a 5, and I've already calculated this one as a 5. So I'm taking 5 minus 5, we get a 0. Okay. All right, this one I know will be 3 out front, 3 times that. So that'll have to be 3 times 10, which is 30. All right, this one will have to be 3 times 0 to 1 f of x dx. And that's a 5, so this had to be 3 times 5, which is a 15. So straightforward enough use of some of those properties of the definite integral.